Hello everyone, I'm Professor Deepika from Department of Electrical and Electronics Engineering from Vidya Institute of Technology. In today's video, we are going to discuss about the laws of illumination. So the illumination is nothing but what like in the module 1 we have discussed about that the electrical energy can be converted into a one type of energy that is called as heat energy. So that means by converting the electrical energy into a heat energy, we can actually obtain the heating effect that will be utilized in the domestic purpose as well as in the industrial purpose. So therefore electric heating and welding are the most applications of the electrical energy. And in the second module we are going to discuss about that how actually the electrical energy is going to convert it into a light energy. That means what, we are going to convert one form of energy into another form of energy, which is very useful for us. So in the module 2 we are going to discuss, that is, electric energy is converted into a light energy. So that light energy when falls on an object, like how actually the objects look like, so that effect will be called as the illumination. So the light is very important in our day to day life, because without light we can't live. So whatever the main thing is that the natural light what we are getting from the sun, this is actually causing the this is actually a good cause, and by which we can actually see the objects properly. So the purpose of using the artificial light is also in this manner, that is, whenever the artificial light, when it is falls on an object, it also must produce the same effect as the natural light. That is, from the natural light, how we are going to see the object, in the same manner we have to see the objects by using a artificial lighting. So this is the purpose of artificial lighting. So to produce the artificial lighting, we are going to use electric energy. So this is what we are going to discuss in this module. So we have so many definitions, and in the today's video we are going to discuss about the laws of illumination. So the illumination is nothing but what, it is actually how much the light flux, or how much the luminous flux is falling per unit area, okay, or whatever the surface we are having, so how much it is absorbing the light energy. So that is actually termed as the illumination. So we have two laws of illumination. So these are very important. So the two laws are called, one is the law of inverse squares and the second one is called Lambert's cosine law. So coming to the law of inverse square law, that is law of inverse squares or law of inverse square law, we can say. So here we are going to consider the two areas. That is, we have a one light source. From that light source we are getting the light, and it is falling on the two objects or two surfaces. Yeah, and here we are considering the area of those surfaces, which are A1 and A2, and they are usually at a distance of R1 and R2 from the point source. Yes, point source is nothing but what, whose dimension is negligible. So that will be termed as the point source, and the two areas A1 and A2 are at a distance of R1 and R2 from the point source. Yes, and from the light source it is having the luminous intensity I, and it is normal to the light rays, and the solid angle subtended here will be termed as the omega steradians. So this is the term we are going to define in this law of inverse square. You can see here, so this is what we are going to tell. So there are two surfaces, you can observe here. So there are two surfaces A1 and A2, and these surfaces are usually normal to the like these are usually in the range of the light. And here this will be the and here this will be the light source years, and the solid angle subtended over here is omega, and S1 area A1 is at a distance of R1 from the point source years, and A2 is at a distance of R2 from the point source years. And luminous flux radiated per steradian is termed as the I. That is luminous intensity. It is represented by I. So luminous intensity is nothing but what? This is with respect to the light source. Like how many luminous flux is radiated per unit solid angle. So that will be termed as, or that will be defined as, a luminous intensity. So that's we have written like this. And the total luminous flux radiated. If I want to know how much flux is radiated, then I'll do the cross multiplication. So therefore, this will be equals to I omega lumens. And next, illumination on surface of area A1. So how do I write illumination on surface area A1? As I told you, as I told you here, the luminous flux or illumination on the surface area A1 we need to calculate. But the area A1, how do I calculate? I can calculate from the formula of the solid angle. So the solid angle can be written like this, that is omega will be equals to area divided by that is the area divided by r1 square. So therefore area can be written as a1 is equals to omega into r1 square. This is r is usually the radius or distance we could take. Okay, so therefore e1 will be equals to omega into r1 square. How I written like this means, like we have the illumination is nothing but how much flux is falling per unit area. So this will be the definition of illumination. Okay, E is nothing but illumination. So illumination will be represented by E, and the luminous intensity will be represented by I, and omega is nothing but what? It is solid angle. So illumination is nothing but flux per unit area. And flux, how do I write? Flux is nothing but what? You can see here, the flux can also be written as I into omega. That is total flux radiated per steradian is nothing but luminous intensity. Then if I interest in the luminous flux radiated, then this will be equals to I into omega. So therefore phi is replaced by I into omega by EA. And now area is nothing but what? It is nothing but omega into r1 square. So this is actually the definition of the solid angle, and hence we have written like this. So here what happens? Omega and omega get cancelled. So thus we have left out with I by r1 square lumens per unit area. So in the same way, illumination on surface of area A2. How do I write? You can see here by the same formula we could write here. That is E2 will be equals to I omega by A2, I omega by omega R2 square. That is nothing but I by R2 square. So, so what I want to conclude here is, or what we can define the law of illumination is nothing but what? So from this definition, you can see here the illumination, what you can observe over here is it is inversely proportional to the square of the distance between the square of the distance between the point source and the square of the distance between the point source and the object or the surface. So this is why we call it as inverse square law. Why we call it as inverse square law? Because in here illumination is inversely proportional. You could observe here illumination is inversely proportional to the square distance. So therefore it is called as inverse square law. So how can I define this? The statement will go in this way, that is illumination of a surface is inversely proportional to the square of distance between the source and the surface. And this completes the first law, that is inverse square law. Next, let us concentrate on Lambert's cosine law. So the Lambert's cosine law, to define this or to state this, let us have some explanation part. Illumination at a surface is maximum if the rays of light falls normally on the surface and decreases if surface is inclined to the incident light. So this is the obvious thing that if the surface is right perpendicular or right beneath the source, then the illumination will be very good. If the surface or if the surface is far away, or it is at an inclined at an angle to something, like inclined at an angle to the light ray, then the light flux falling on the surface will also reduces due to some atmosphere effect and all, because there will be a gases, something will be there, so that some part of light will also be consumed by the atmosphere, and we won't get the full we won't get the full illumination on the surface. So therefore, if the surface is right beneath the source, then we will get a maximum illumination. If the surface goes away from the, or if the surface is little far away from the, or inclined at an angle to the light source, then the illumination is going to reduce. So to define this, let us see. Consider a small element of a surface AB, which is normal to the beam. You can see here. So from this diagram, you could see here the AB, what you can observe. So this is the surface. Okay, so this is the surface which is inclined. Which is perpendicular to the light source. Here P will be the light source. Okay, here P will be the light source. So from the light source, you can see these are the light rays we are getting from the light source, and I'm taking the surface AB. So this surface AB is perpendicular to the light ray. You can observe here it is perpendicular. That is the angle between the surface AB and the light ray. What you can observe here. So this is perpendicular. Okay, this is perpendicular, and illumination on surface AB. So then how do I write the illumination? So I can write the illumination from the illumination first law. So therefore EAB is written as I by D square. That is, by this statement, or by this inverse square law, so I can write the illumination in this way. That is, the illumination EAB, that is illumination on the surface AB, is equals to I by D square, whereas I is nothing but the luminous intensity, and D is the distance between the point source and the surface. So you can see here, so this small letter D is the distance between the surface and the source. Hence we can write this as EAB is equals to I by D square. Next, if phi is flux, then I can write EAB as phi by area AB. So this EAB, whatever I have written, so this is from the inverse square law. So right now we have discussed it. So this equation 1 I have written from the inverse square law, and this is AB is nothing but phi by area AB. So this is actually from the definition of the illumination. That is, illumination is nothing but flux per unit area. So that I have written over here. So next, illumination on surface CD, which is normal to vertical axis and inclined at an angle theta to the beam of light. So here I am considering the two cases. One thing, the surface is normal to the light ray, and the another thing that the surface is inclined at an angle to the light beam. So therefore, you can observe here. So this is the AB. So this is perpendicular to the light beam. And now you can see here, so this CD is the surface. Okay, so this is the CD of the surface, and which is normal to the vertical axis. You can see here, this CD is vertical to the normal axis. That is, the angle between the vertical axis and the CD is 90 degree, and it is inclined at an angle theta to the beam of light. So you can see here, so when we consider this thing, so this will be that is, the surface will be inclined at an angle to the light beam. So this is the consideration I am going to take. So hence I can write the illumination on surface CD as by the definition of illumination, that is flux by area CD. But the area CD is nothing but area AB by cos theta. That is, if I consider this triangle, Okay, so if I consider this triangle, the if I consider the triangle, usually the cos theta, what you can observe over here. So this cos theta is nothing but what it is, area AB by area CD. So here something like see, area CD will be the hypotenuse, and area AB will be the adjacent side. Hence, I can write area CD as area AB by cos theta. Hence, I can substitute in the equation 1. That is, from the equation 1, I can write ECD as I by d square into cos theta, because area AB, 5 by area AB, what we are having, so this can be replaced by I by d square. So this is nothing but cos theta. I can write ECD in this form also. So again, I am taking the same figure for the consideration, and you can see here the cos theta. Okay, so this is the theta angle I am taking. Okay, so this is the theta angle I am taking. So this is the triangle I am going to consider. If I consider this triangle, you can observe over here. So this is the triangle. So from this triangle, cos theta is nothing but h by d. That is, cos theta here, it is adjacent by hypotenuse. So therefore, this is nothing but adjacent is nothing but h, and the hypotenuse will be d, or d can be written as h by cos theta. That is, distance between the source and the surface can be written as h by cos theta. Now let us substitute the d value over here. So the d can be written as h by cos theta. If I substitute over here, it becomes h square by cos square theta. So cos square theta will go to the numerator. Hence, it will become cos cube theta. Therefore, ECD is nothing but I by h square into cos cube theta. So what I can define from this from this expression means, illumination at any point on a surface is directly proportional to the cosine of angle between the normal at that point and the direction of luminous flux. So that is nothing but what this like if the surface, if we take, okay, so if the surface, if the illuminate if I want to know what is the illumination on the surface, which is inclined at an angle. Okay, so to know that, how can I define the illumination at any point on the surface is directly proportional. You can see here, it is directly proportional to the cosine of angle between the normal at that point. So this is the theta angle I am talking about. So this is the normal drawn at this point. So therefore, this is the angle between the normal at that point and the direction of luminous flux. So this is the direction of luminous flux. Okay, and this is the normal drawn. So this angle will be called as theta. Hence, the illumination at any point on the surface is directly proportional to the cosine of angle between the normal drawn at that point and the direction of luminous flux. Hence, we can define this. Next, in the next video, we will see the problems related to the problems related with this. Thanks for watching the video.